Let's just wait for a couple of minutes, maybe 1 or 2 minutes, and then we can get started. Awesome. I think we can get started. So thank you, first of all, for coming to this talk. And I'm Arun. I'll be talking about LLMs today, the large language models, which have got pretty recently a lot fame. So let's get started. Uh, so I work for Google, and basically I work for search ads. So when you search for something on Google, like iPhone or something, and the top ads that you see, my team is responsible for building that. And so I mostly work on generative AI and large language models. So that's why I thought like this topic seems like a really good fit. Uh, so let's jump into it and maybe set some expectations about the talk. So no work talk. I'll not be talking about any of the work that I do in Google, and the things that I talk about. These are not Google's opinion. So let's get that out of the way. Then this talk is supposed to be a little high level. The primary goal is to build intuition, and there are going to be a lot of mathematical inaccuracies for sure. But the idea is to not dwell into the details, but rather learn the motivation behind the work that is going on and the direction that we are heading in. The talk is going to last for 30 minutes, and there's no homework at the end of the day. So, no tasks, just enjoy, learn, and ask questions if you have any at any point, and I'll try my best to answer them at the moment. Okay, awesome. So, let's get started. Okay, so these are the topics that we are going to talk about today. We'll start with neural networks, then we will jump into embeddings, then we talk about the famous attention, then large language models, maybe touch upon a little bit of multimodality and what are the products that are using LLMs today, and then a little bit of where we are standing today and where we are heading, and what are the interesting things that are still open in the field. Okay, so let's jump into neural networks. So I think I'm not sure how many of you are familiar with neural networks already, but I'm guessing these are pretty famous by now. So I'll just touch upon that. Maybe this can be a refresher for you folks. Okay, so neural network is just a big mathematical equation with a lot of linear algebra and a special type of function called activation function. These are not linear function. This is not linear algebra is slightly different, but we can assume that these are just fancy functions which take in some value and return some value. So that's good enough for now. So in this neural network, we see it takes in three inputs: variable one, variable two, variable three, and then it has a lot of parameters and in the equation W1, W2, and so on until W8. And then we return or generate some kind of output, right? So this is just an equation. Output is represented as equation where variable one and variable three, two and three are part of the equation, and a lot of coefficients are also part of that equation, and these like these W1, W2 to W8. So when we talk about training a model, we basically talk about finding values of these W's in such a way that the output of this equation is as close as possible to the expected output for a given data set. So the key part here is given data set, right? we cannot solve a equation globally, but we can try to solve it for a data set. And the technique to do that is gradient descent. So I've also tried to highlight the key takeaways from each slide in the orange part. So try to focus on that. So for this, especially like in this slide, we are talking primarily about a data set. So data set matters a lot. So bigger the data set, the more generic equation we can build, a better equation we can build, and hence we will have a better model. That's the key takeaway. So okay, let's jump into the meat of the problem, right? Uh, can we generate text from neural networks? And the answer is yes, right? We already see this happening. So let's talk about how it started and how would no like a new person would do this. So let's say if I were to build a model that predicts next character, like what would be the next character in the sentence, I would probably start with a like a simple neural network, pass all the previous characters in the input and ask the model to generate a new character. So for example, here I'm passing HELL as input, which like occur at 8th, 5th, and 12th place in the alphabetical order. And I'm asking the model, like, can you generate O? And the model will do it, right? The model can predict, and that this works fine. If you look at history, like until 10 years back, a lot of models used to work on this kind of approach where they would predict the next character or they would predict the next word just based on the input without any magic going on between the neural network. This is a plain, simple neural network as it can get. So it is possible and it can be done. But the question is, why is it bad? Like, why do you need fancy techniques? Why do we need large language models? Like, if this works. And the problem here is that it works, but not works that great. For example, like in this example that is on your screen, when we give the model input hell, the model does not know that the next character would be O or would it be a full stop? Because this can be a end of a sentence as well. Like for example, if the sentence can be go to hell, right? Or the the word can be hello as well. But the model is very like model would not be able to figure this out. And the primary reason behind that is because there is no semantic learning going on here. And what do I mean by semantic learning, right? So the inputs that we are passing to the model right now are what? If you see, these are just random numbers, right? Like 8 is a random number, 5 is a random number, 12 is just a number, and these numbers are just in the order in which these characters occur in the alphabetical order, right? And they don't have any correlation. Like if B occurs after A, does that mean B and A are very close to each other? Does that mean that? No, it does not, right? Like, do you see a sentence and whenever you see A, is your hunch to write B next character as a next character? No. So that's not true, right? And that's the core crux of the problem. The inputs and the outputs, like they don't have any semantic relation between them in this modeling or in this approach of building a text generator. So how do we solve this problem? This is where embeddings come in. Embeddings is a beautiful way to represent a word as a long repeat list of floating values. So for example, here, if we see a sentence called let's buy Apple iPhone 15, the word Apple can be represented by a long list of floating values. And these can be like 0.1, 0.2, dot, 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 like can be like have n values here, and they can be like between any kind of dimension space. Like they can be like from -1 to 1, 0 to 1, whatever the way you feel more comfortable. But the idea is representing a word with a big list of floating values. Okay. And the question is like, how do you build these embeddings and why to build these embeddings? Actually, that's also another question. But let's talk about how to build these embeddings. So in 2013, Google came out with something called Word2Vec. Word2Vec is a way to generate these embeddings. So if you see on the left side, like in the screen, you see the input to the models are let's buy iPhone 15, and the Apple word is missing. So the idea is, can you predict or build the embedding for the word Apple based on its neighbor in the sentence? So that's the core thing that we are trying to solve with this neural network, and it works great actually. So the answer is yes, you can build embedding of Apple based on the embedding of its nearby words in the sentence. So for example, at the bottom you can see embedding of Apple would be much like it would be close to embedding of let's plus embedding of buy plus embedding of iPhone, da 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 da. And you can build this kind of embedding. So I think the key part, one of the key part that I want to gently touch upon is like the softmax layer. This is like like a mathematical thing, but to explain in simplicity, I would say softmax layer can be considered as a way to convert an embedding into a prediction. So given an embedding, you identify what is the word most closest to it. So for example, if the intermediate layer, it says embedding XYZ, the softmax will return you, does it mean Apple or does it mean iPhone? Does it mean 15? These kind of things. So this is like not a complicated thing, but just to keep in mind something where maybe we will reference it later in the slides. But yeah, so this is word to vec. And what does this give us? This gives us that floating vector that we were talking about earlier, right? So let's see why embeddings are necessary and why are we trying to build embeddings actually. So once we have created embeddings for each word, the thing that happens is that now you can do a lot of algebra with these embeddings, and that's the core like thing that you get out of the embeddings. So for example, let's say if you use word to vec and you build embedding for each word in the world, let's maybe there are 300,000 English words and you build embedding for each of those words. And then in the space, like when you use these embeddings and analyze them on a graph, let's say, you would realize that the embedding for the word king is much closer to the embedding of the word man, and the embedding of word queen is much closer to the embedding of word woman, right? And that's basically, and how do you say close in mathematical terms? You basically use like cosine similarity or dot product, which is like a simple mathematical function. So dot product of queen comma women would be much greater than dot product of queen comma man, because queen is much closer to women than men. And that's the algebra power that you get out of building embeddings. The other thing that you can also do is that when you do some kind of plus and minus, additional addition and subtraction, embedding king minus embedding of man plus embedding of women will actually give you something close to embedding of the queen. And that's basically now you are able to do a lot more mathematics on words rather than just representing them with random numbers, right? And that was the thing that we were trying to solve initially. Like these were random numbers. This is 8, this is 5, this is 12. And this is not the case anymore. Now we have a big long list of floating values that represent these words, and they make more sense. Any if you have any questions, just ping those on chat and I'll try to answer them. So moving on, uh, like there's a big problem in what we have built, in what word to vec built actually. The problem is, let's go through two examples. The first example is, or the first sentence is, let's buy Apple iPhone 15, and the another one is, let's buy an apple pie. But when we built these embeddings, we built one embedding for a word. So the word apple would have the same representation. So every apple in this world has the same embedding. And that's a problem because these two apple are pretty different. Apple pie is very different from Apple iPhone, right? And that's the new problem that arises with building these global embeddings. How do you solve this problem? And this problem is solved by building contextual embeddings. And what is a contextual embedding? This basically means like every word in the sentence would have a different embedding, uh, and that embedding would be determined by the neighboring words, basically the context in which the word is used. So for example, here the word apple would be built by the word that are next to each other, like let's buy iPhone 15. These are the words that would represent apple's embedding. So that will capture the context. So let's go jump into that. Okay, so this might look a little scary, but this is not at all scary. So we'll go through this diagram step by step and maybe try to understand what is actually going on, what is a contextual embedding, and how we are trying to build it. Okay, so let's start at the bottom of this chart. We are at the bottom layer where we have the words, and we have already built the global embeddings that we were just talking about using word2vec. And these embeddings are like there's one embedding for one word and it's global. There is no context. So what we do is we would try to create a new contextual embedding for the word apple with using some fancy math. And that's how this is how it goes. At the bottom, we have all the words, then we have their global embeddings, and then we will take a dot product of the global embedding of the word apple, which is W3, with all the other embeddings in the neighboring in the neighbor of this word. So for example, like here we are taking W1 with W3, the dot product, and W2 with W3, and W4 with W3, and W5 with W3. So you get a numerical value basically, and this numerical value shows you how important the context between these the word apple and the word in the context are. So for example, like the point 3 would tell you how close or what is the context between apple and iphone, and that would be much more higher than the context between the word apple and, let's say, the word let's, because let's is a generic word, no one cares about it, right? Like, so the value would be zero point 0.1, but the word iphone is actually a very important word because this differentiates this apple and the apple in apple pie. So the value would be much higher here. And once we have figured out these values, these numerical values, we just add all the embeddings, the global embeddings that we have built in the proportionality of these weights, and this gives you a new embedding for the word apple. So initially we started with W3, now we have W3 dash, and W3 dash is just a linear combination of uh, other words in my neighborhood. Cool. So I think one of the key takeaways here is that when you're building embeddings, especially these contextual embeddings, you build to build one embedding, you take on of time, which is you need to take a look at all of your neighbors, right? So if you want to build embedding for the whole sentence, like every word in the sentence, the time that would be taken to do this would be on square, which is like quadratic in some sense. So that's why these models actually take a lot of time when the sentence is huge to do the prediction. So that's one thing that to keep in mind, the quadratic nature of the prediction here. Okay, so let's jump into the main crown of the LLM space, which is attention. And what is attention? Basically, we built some contextual embedding, right? Can we improve it? Can we make this better? Is the real question that we are trying to answer with attention. And the answer is yes. And how do we do it? Just brute force, basically. And the brute force is just adding more variables in the equation. As you see, the parts that are highlighted in orange are the new coefficients or new tunable parameters that we add into the equation. So we start with as we were starting earlier, we start with global embeddings, then we add some kind of positional embeddings. These are we can assume for now that these are another variable that can be added in this equation. And then we have wk, this is another set of tunable parameters, and then we have wq, another set of parameters, and then wv. And basically at the end, this is very similar to the contextual embedding that we started with, but tons of new parameters in the equation. And this works really well because you have way more parameters in the equation, so you can tune them more. And if you can tune them more with a lot of data, then you definitely are going to get more results. So this is kind of a brute force approach. Just by adding more and more tunable parameters, you get better results in this sense. Is this in this context? Okay. And as we discussed in the first slide, you can solve these tunable parameters by training your model on a given data set, right? So that's basically the crux of the thing, that attention is just a more complicated and, let's say, a brute force way of generating these contextual embeddings than the trivial way that we discussed earlier. Cool. So now we have established some kind of baseline. We know what is a neural network. We know what are embeddings. We know what are contextual embeddings. Now we also know what is attention. So we can jump into the next big thing, which is decoders. What is a decoder? So until now, we just talked about how to represent a word, right? How to represent a word in global sense. How do we represent a word in contextual sense? Now we talk about how do we actually generate the word, the next word, let's say in the sentence, which is the core problem that we are trying to solve. And that's where decoders come in. So this is a decoder block, and the idea is very similar. Just exactly like the same that we discussed in the previous slide. This is just the attention block that is here in the orange. So every word goes into as an input, and under the hood, it converts them into contextual embeddings, and then there is a neural network on top of it. And this neural network generates new embeddings or modified embeddings, and then we convert these embeddings into a predicted token. And this is where I was mentioning earlier in the previous slide that softmax is a mathematical function that converts embeddings into tokens. So we use softmax, and we generate the next possible word, which can be, let's say, like today. So that makes sense, right? Like, let's buy Apple iPhone 15 today. And once this word is generated, you can pass this as an input again to the attention block. And then you can keep on repeating this and keep on generating as many characters as you want until and unless the model generates like an special token or calls it a day by generating some random token that you consider it as an end of sentence. Obviously, while generating these tokens, model can make mistakes, and model do make mistakes. For example, model can generate the word today twice. This is called stutter. The model has a problem, and we can resolve this by some kind of post-processing algorithms, and we can fix these the words that are generated and formulate a better sentence out of it. But the key takeaway here is that a decoder works one word at a time, or one word or a token at a time. So it generates one token, and then it goes back and starts the decoder computation again to generate the next token. So that's the crux of the problem. So coming to large language models, finally the thing that we wanted to talk about, right? So large language models are basically just these decoders stacked up on top of each other, and there are a lot of them. So for example, like some of the models that were built by OpenAI, there are like 120 decoders on top of each other, and that's how basically you end up with uh, trillions of parameters in the model, right? So one thing that like we can talk about is like GPT-4 or GPT-3, like ChatGPT. These models have embeddings, the initial embeddings that we were talking about to represent the word. These embeddings have a size of 12,000. So one word is represented by a list of 12,000 numbers. So imagine how big that is, right? And everything that is built on top of these embeddings, like these attention blocks or these decoder computations and everything, that has to be in some sense linear to these embedding size. So the bigger the embedding size, the bigger the size of the model and the number of parameters in the model itself. So that's how you end up with, you start with 12,000 size embeddings, and then you end up with like trillions of parameters. Okay. So the thing is that because this model is so big, it will take a lot of time to train, and it'll also require a lot of data to train as well. And that's like the other class of problems that we start running into. So just going through some news, I learned that like OpenAI spent $100 million to train GPT-4, and that's because it took months to train because there are so many parameters in this equation that that you just need to keep like turn on the training and leave it for months in some cases, right? So that's basically the crux of LLMs, and this is how they work. Let's jump into maybe a little bit of multimodality on what is multimodality. So just building upon the basis that we have already set, which is embeddings. Let's think about, can we build embeddings for other kind of content? Like we know that we can build embeddings for words or text. Can we do that for audio? Can we do that for video? Can we do that for images? And the answer is yes, we can do that, and we have been doing that for a long time. And the core problem here is to get a kind of a data set that gives you the notion that these two content are related. So for example, if we were to build embeddings for images, then we would need something like, is this text related to this image? And if the answer is yes, then we will plumb that data through this model that we have in front of us. Text would be content A, image would be content B. We would pass them through an encoder. This will generate a embedding which is specific to that content, and then we will also generate an embedding for the image, and then we will have something in between. Let's call it a universal embedding, and this model will try to predict that these two things, these two embeddings, or the output of encoder A and output of encoder B, are actually similar to each other, because that's what our data set said. And you and similarly, you can have rows where the text and image are not related to at all each other. So for example, if you have the word dog and the image is about cat, then the model should predict false. And in the cases when there is an image of dog and there is a text dog, then it should predict true, or predict that these are similar. And this is the process that you do to generate some kind of universal embeddings, an embedding that can represent both text and image. And this approach is called contrastive learning, but we don't have to get into that, like the approach and all. But the beautiful part here is that these kind of things and these embeddings are actually responsible for image search. So if you have iPhone and you search for in your photos gallery, if you search for like car or something, and it gives you the images of the car, this is how it is doing it. In the backend, they generated an embedding for the image, and they generate the embedding for the word that you search for, and they figure out, okay, which of these two embeddings are similar, closer to each other, and they find all the images that are closer to your text embedding, and then they return those images to you. And that's how like the Google Photos, or any like Apple Photos, and all these products work actually. Awesome. So that's it for multimodality. I'll not get into much like more details. So I also wanted to talk a little bit about products, because I think we are in the phase where a lot of LLMs are being used for really new stuff. So I see the products that are surfacing in the space in three categories. Primarily, like LLM as a service is being offered by tons of companies today. Like Google is providing Gemini, OpenAI has ChatGPT and other GPT models, and Mistral AI is one small company that has popped out of France. They are also doing like really great work. And then there is Meta with LLMs, Llama series, which is like publicly open source available models that you can use. And then these LLMs as services are actually being used by tons of companies to build user-facing products. And when we talk about these user-facing products, I see two trends. Like one is where we are building products that were never possible before at all. So for example, like Character.ai, Perplexity.ai, these are really famous companies. They have 160 million monthly active users. Perplexity has like 10 million monthly active users. And these are the kind of companies that were never possible before the LLM world, because the model were not really that smart. And so these companies are like $1 billion worth, came out of nowhere in just in last two years, right? So exceptional products. And then on the other side, we see some incremental improvements also happening. When I say incremental improvements, I don't mean that these improvements are slow. Definitely these improvements are going crazy, but I think the core idea is not new. So for example, we now have a better way to generate code, and that's like a product provided by GitHub called Copilot, and you can now generate the code, or like small piece of code, or maybe one file code based on autopilot, and you can just write comments and it will generate the whole code piece for you, etc. And so I think this was slightly possible before. Like there were techniques to do it, like autocomplete, and then there were simpler models to do this. But definitely a lot of improvement has been made in the last 1 and 2 years. Right? And then there is RAGs, which is better use of vector databases. And databases is nothing but a data store that stores all of your embeddings in some fashion. Vector databases were around for a very long time, but all of a sudden, like in the last 2 years, a lot of good use cases of vector databases are coming out based on RAGs. And then there is the plain old use case of generating text and images wherever there is a need. So, for example, DoorDash uses these models to generate descriptions for the dishes that are provided by restaurants in case the restaurant has not provided all this kind of information. So these kind of things are also going on. Cool. So I'm really excited about the product space. I feel a lot new ideas and a lot new companies would pop up. I did not mention all of them, but just to give you some stats, like if you are familiar with Y Combinator, I think the last batch of the Y Combinator contained like 85% of the companies, 80% of the companies were building something with large language models were in the AI space. So you see how crazy the space is. And at this is basically the final slide of the presentation. I want to leave you with some kind of parting thoughts and give you some kind of idea about where we are today and what is blocking us from, let's say, the building the model that can answer everything, the holy grail, the uh, artificial general intelligence. Basically, we can say that. Uh, so yeah, I think the first problem is hallucination. So we did not talk about it much in the previous part, but hallucination is when the model generates a word that is not expected and you unwanted words basically. And a lot of research these days is being spent in building models that do not hallucinate because hallucinating models are very good for creative use cases, but not they are not really great uh, source of factual information. So you can't replace, let's say, like Google search or maybe like news media articles, etc., just by a model because model can generate random stuff. Model can generate stuff that you don't want. So they're basically not that suitable for getting medical advice from, for example. So there's a lot of research that is being done in the space. And the other problem today is we want to build bigger and bigger models. So OpenAI recently announced that they are going to build, I don't know, like thousand trillion parameter model. So can we do that? Do we want to do that? We don't know that yet. Can we keep building bigger models? So I think uh, so from what we already know is that smaller models are still useful. They're still more economical. So if you want to solve some kind of problem, some small problem, for example, given photos, you want to predict if this is a cat photo or this is a dog photo, you still want to build the old school CNN models instead of using multimodality from some fancy model out there because it makes no sense. Small models are going to be around for a very long time. They are going to be there until unless we solve the economical problem that comes up with these bigger models. So when we talk about building a bigger model, we also need to think about how can we like actually build a bigger model, because bigger model does not mean just adding more parameters, because if you keep doing that, uh, you will run into a problem where the new weights or new parameters that you're adding into the equation are just redundant and they can be removed. And that's very actually that was demonstrated very recently by a couple of open source models where you would see that Llama 3 from Meta, which is a 70 billion parameter model, was actually beating a couple of models that exist in the industry, which are like 100 billion plus, which basically means that you didn't need those many parameters to begin with. It's just that Llama did a better job of training the model. The Llama team did a better job, and even with the limited amount of parameters, with 70 billion parameters, they were able to do a better job in comparison to the 100 billion plus parameter models. So the other thing is like the model, the data that we feed to these models also play a very important role, right? You can't keep throwing shit at the model, and the model will, like, it's this bad data in, bad data out kind of a stuff. So you want to like curate your data set very meaningfully. And these like this is a bigger challenge actually. Like people do not see it uh like more often, like like from news and all, but build like getting more meaningful data is really a big problem. Like most of the models that we see are these days are trained on internet data, but getting like meaning out of that internet data is actually the core problem out there. Increasing parameters is probably a simpler problem to solve, because lately we have not been coming out with new model architectures. But I think this is one of the problems that people run into. Okay, so when we talk about building a bigger model, we also need new architectures. We can't just like, as I said, like I said that we can add more parameters, but we want to keep things economical as well. So when we want to keep things economical, you have to come up with better architectures. So there are a couple of things going on in this direction called quantization, blockwise decoding, flash tension. These are just like terms that I mentioned, but you can follow up and read about them online. These are really cool techniques. For example, I'll just talk about quantization for a minute. Quantization is just building a model that does not have floating values as parameters, but instead they use integers and like small 16-bit integers, etc. So that what ends up happening is that your model uh, is smaller in size now, so it can be trained faster, but it will definitely have some kind of accuracy loss. But it's one way to reduce the size of the model. So that works really well actually. Cool. Another problem when we talk about like increasing the size of the model is hardware failures. So if you, I'm not sure if you have read the recent paper that came out with I think Llama 3 or 2, where they trained Llama models on the public available data set. And one of the key insight that they shared was that most of their failures during the training were actually attributable to hardware. So hardware is a really big challenge. So when you start a training job on your model, it sometimes fails just because there was a hardware failure. And that happens a lot in case of these large language models, because the model is distributed over a lot of chips, right? And when you have a model distributed over a lot of chips, even a single one of them fail, then the whole training task fails, and then there are you need to debug it, etc. And that sets you back. And the more chips you start using in parallel, the more chances of the failure are. Is just like probability of failing multipliers with every chip you add into the system. Okay. So, and the other problem is that these models are really big. So think about GPT-4, for example. GPT-4 is a model that has 1.3 trillion parameter in the equation. And each one of these parameters is what? At the end of the day, it's a weight, right? And weights are what? Floating values. So you can imagine like these models turn out to be like in GBs on size. And you have to put this model into some RAM, because at the end of the day, what is happening? You are forget about all these complicated things, but at the end of the day, when we talk about the basic computer science, what is happening? There is a list of numbers in RAM, and there is a CPU, and then the CPU needs to like run some multiplication and addition to give you some values, right? So when you want to run this equation or this computation on GPU, you need to transfer those weights, those floating values from the GPU RAM or the TPU RAM to that compute chip, which basically means you're just transferring data from kind of RAM to CPU. But we are in an era where this has become a bottleneck. We never thought about it earlier. And when we were just using our laptops and MacBooks, this was not a problem. But this has now become a problem all of a sudden. In the last 2 years, NVIDIA and there is a company called Cerebras, which have come up with like crazy chips. So if you see on this image that I've added here, this chip from Cerebra, it's actually 21 centimeter by 21 centimeter. It's like this big. So they are building these kind of chips to support data transfer from the RAM to the this compute part of the GPU, like the bandwidth between them or the data transfer speed between these two units are actually in petabytes per second, like double digit petabytes. This is insane. This has never been done before. And this all of this is possible because there is so much interest and so much funding in this space. In just last 2 3 years, these things have come out. So it's crazy. So, but one of the fundamental problems is like we can't just make bigger and bigger chips. Nvidia can't just like throw more money and just ask to build a bigger chip. Why this is 21 by 21 centimeter? Can we go 30 by 30 centimeter? Why not do that? Like let's start 1 meter by 1 meter or something like that. You can't do that. And the reason is physics won't allow you to do that. So first problem that occurs while doing that is because at the end of the day, this is just one chip, and that is like the chip manufacturing technique does not allow you to do that. Like the bigger the chip is, the more chances of the failure that happen. One no-brainer thing that we can think about here is that when once we start running some kind of computation on these chips get a lot of heat. When there is a lot of heat, there are going to be a lot more failures because at the end of the day, this chip contains just small microscopic transistors. And these, when there is a lot of heat, some of those transistors might fail, and it's quite likely that they will fail. That's just normal physics, right? And if there is more heat, these equipments on the chip may expand. That might lead to also some more failures. And there is a lot more energy consumption when you build a bigger chip. So you need tons of cooling equipment, etc. So the approach is not like simply scalable, but I believe that because there is so much interest in the space, there would be new and new architectures that will come out. And maybe we might have a breakthrough where we don't need such bigger chips, but maybe we can build a bit like maybe we can come up with a better technique there. Cool. So I think these are the interesting questions. One of the last thing that I want to leave you with is one of the things that Sam Altman said a couple of months back, I guess. And his thought process was that with over time, the number of people that we need to build unicorn companies or the companies that are, let's say, above $1 billion, uh, have been decreasing slowly. So you need less and less people to build bigger and bigger, more impactful companies. And maybe we are in an era where a single person can actually build $1 billion company. That's really exciting. And so I think that's basically what I want you to like part with. We are in very exciting times, and there is a lot of interest in the field. And I think we might see a lot more things and a lot more creative solutions coming up. So yeah, I think we should watch out for this field. That's it from my side. I would love to answer any questions if you have. Let me know. Yeah, that's it. That's it from my side. Awesome. I think I've put out the slides in the chat as well. So if someone wants to take that. And I see a question by Jay. So yeah, okay. So you were saying that also Queen does not always refer to royalty and a royal maybe more than a queen. That's true. Actually, that's true. This is just an example where we are trying to. The idea is to not understand that queen and women and king and man are the only thing in the space. The idea is to understand the relative distance between the things, right? So I agree. Like with the example that you're talking about. So any thoughts on regulation regarding LLMs? Yes, I do think that we need more and more regulation, and I think it's as a like there is a lot more at stake when we talk about bigger companies. So, for example, like let's talk about OpenAI, right? OpenAI is kind of leading the field in let's say LLM space or maybe some other company, maybe we can talk about Meta, for example, is leading open source LLM development space, right? I think these companies have some like responsibilities on their shoulder, because since they are leading this space, they need to be the one who like actively participate in building more regulations and building more thoughtful solutions, uh, because they are the ones who are going to see the problem before everyone else, right? The research that we often see comes out a little late. Maybe it's by like 1 or 2 years later when the things have become cool. So I think, yeah, I think regulations are way more important than we think, especially in terms of like video generation, image generation. This is where I think we need to be more thoughtful. I think text is still okay, but we definitely need things here as well. Yeah. Awesome. I guess no more questions. So okay, so I'll be available on Discord as well. So if you have any questions regarding the slides or the presentation or anything related to the hackathon, so I'm very excited to be part of the hackathon. I'm one of the judges. So if you have anything that you're trying to build in space, in the AI space, or if you feel if you need any kind of help in normal software engineering, anything, just ping me on Discord, and I can help you wherever I can. Okay. It was nice presenting. Have a good day, folks. Bye.